Rich spoke a couple days ago about the value of self-imposed constraints. Swearjure is the subset of Clojure with no alphanumeric characters. This expression here computes 7 factorial. So the primary researchers on this project are Tim McCormick and Jean-Nicolas Larange, and most of the content in this presentation comes from them. So what sorts of things can we express in Swearjure? To start with, we can get any positive integer we like, starting with the fact that the multiplication function returns 1 if you don't pass any arguments. So you can add these ones together and then multiply those larger numbers and get anywhere you need to with that. You can get negative integers and ratios using the negation function and the division function. We don't know any way to get floats. If we could get a single floating point number, presumably we could get the rest of them, but don't know of any way to do this yet. True and false are pretty easy with the equals function, and nil we can get by calling an empty hash map with something that's not in it. Data structures are interesting. Most of this is based on what you can do with the backtick. So on line 3, we can con something onto a list by using a backtick quoted list and then unquoting a single element and unquote splicing a sequence. You can concat two things by unquote splicing both of them. We can convert stuff to a vector by unquote splicing it inside the vector. And we can do something mostly like inf by converting it to a vector first and calling that vector using an integer in the style from the previous slide. So this requires that your sequences can all fit in memory nicely. Functions are where it gets really interesting. Because the only function literal we can use is this reader literal. We can't use fun and defun for obvious reasons. And even with inside of this, we can only refer to the first argument and the rest of the arguments. We can't refer to the other positions. But that turns out to be okay because we can always take the rest and stick them in a vector and call that. And really crucially, we can't nest these. One problem that comes up is how could you return a data structure literal from one of these functions? You can't just stick it in there like on line 1 because it'll try to call it. You can do this with fun, but we can't use fun. You could call identity, but you can't call identity. But what you can do is you can stick it into a vector and then call that vector immediately and pull it back out. So this is a useful tactic. Other common Clojure core functions, inc and dec, are pretty easy. Identity uses the tactic from the previous slide. Put the argument in a vector and then pull it back out. Boolean is quite useful for when you need to simulate if. Fortunately, you can create a map of all of the falsy values and then call that map with true as the not found value. So that lets you convert something into a Boolean. Line 5 is the high-level version and line 6 is the actual version. So for control flow and recursion, the best tactic so far is to use a function table. All this code is high level, of course, but hopefully a somewhat straightforward translation into real Swearjure. The idea is that all the functions that you might call, you stick them in a map, and then that map is your function table and gets passed into every function as the first argument. And that function can do a few things and decide what it wants to call next and then pull the function out of the map and call it with the function table again and whatever else it wants to pass in. You can use this to simulate if. So on line 6 here, we're calling if with the in less than 5 expression. So we pass that into the hash map to get a key that we look up in the function table to get the next function we want to call, and then call that with the function table and the other argument. So this is pretty useful. However, it eats the stack pretty badly. Every time you call another function, you're adding something to the stack, and you never get that back. So when we use Swearsier in production, we just try not to think about this too much. Other interesting things, this version of hash map is really interesting. We're doing the stick a thing in a vector and pull it back out tactic here. But inside the vector, we have a back-quoted hash map literal, and at the syntactic level, this has two things in it. But if you're calling this function with, say, 8 things, 4 keys and 4 values, what you're going to end up doing is unquoting the first key as the key in this map, and the other 7 things as the value, and it somehow expands out and you get the correct hash map. So that's really weird. Also, you can get a gensim just for fun, and this expression computes a constant gensim, so every time you call it, you get the same one. So it's not very useful as a gensim, but if you like looking at gensims, you can get them. If you have this function literal in several places, you'll get a different gensim in each place that you create it. But also, Tim implemented rest, which is a useful function to have. This basically does some sort of weird recursive thing with a vector where it walks through the whole thing to build up the rest of it. Yeah, so it's a little tedious, but it works. So what are the limits of what we can do? Is it Turing complete? The first thought everybody has is, well, it's just lambda calculus, right? Well, that's not so obvious, actually, because we can't nest things. They're not really closures. So I don't think there's any straightforward reduction there. However, I've become about 98% convinced that we can implement the SKI calculus if we want to. I would have done it myself, but I don't have time. So please let me know how that goes. Is it Clojure complete? Hardly. There's lots of things we're missing. There's things we can't express, like floating point numbers and other things. We can't do Java interop. Lots of higher order stuff and other host things. Basically everything we can't do. So we're left with the inescapable conclusion that Swearjure is basically useless, but still surprisingly powerful. So work in Swearjure is ongoing. If you're using it in production, then please let us know how it works. There are lots of ways to help. For example, we need help strategizing with how to sneak changes into Clojure that make Swearjure more powerful. So that's all I have. Thank you very much.